Okay, so the last case that I did, I looked at the fact that we could have a repeated factor, x plus 2 and x plus 2 quantity squared. We could also have a case where we could conceivably have a non-reducible factor. I'm putting another one up here, and I'm going to look at this and say, well, first of all, we need to know whether or not the denominator is factorable. And it's useful to have a knowledge of synthetic division here if we want to know if that is divisible by any factor, so that we can, write parentheses around something and something else. Then the factors have to be related to this plus this 4 right here. So the only things that could possibly be factors here are plus or minus 4, because 4 is a factor of 4, plus or minus 1, because 1 times 4 is 4, and plus or minus 2. Those are the only possibilities. When we see the 4 right there, that tells us the last things multiplying together have to be able to give us 4. And the only way we can get that is either by 2 times 2 or 1 times 4. Those are the only ones that are possible. Now, to check what it is that divides that, we use synthetic division because we can do it fairly rapidly with synthetic division. And what I'm going to do, and I hope everybody remembers synthetic division, I think we did it some in class, okay, is write down those are the factors. I'm going to put here, I'm going to choose one of these in the middle. I'm going to choose to do 2, okay? And if it's 2, then what happens here? Well, the 1 comes straight down. So saying 2 here is suggesting that x minus 2 would be a factor, something this would factor into. Well, 1 carries straight down. 1 times 2 is 2. You add those. 3 times 2 is 6. You add those. 2 times 10 is 20. You add those. Now, a couple things that happen here. One of them, notice we don't get a remainder of 0. If it's a true factor, we'll get a remainder of 0. We didn't, therefore it's not. But not only that, that means we can knock out 2 as being a potential factor, but also we can knock out 4 as well. Why can we do that? Well, and I'm not going to mark out the entire 4, but the plus 4 and the plus 2 are no longer possibilities, because when I put plus 2 here, these numbers were all positive and they were getting bigger. That means if I was to put 4 here, they'd get even bigger. So it wipes both those out. Okay? So I went from having 6 potential roots to now only having 4 potential roots, and now I'm going to go with negative 2 and see what happens with that. I carry the 1 straight down. 1 times negative 2 is negative 2. I add these. Negative 1 times negative 2 is 2. I add these. 6 times negative 2 is negative 12. I add these. Okay. Again, negative 2 doesn't work. I know that because I didn't get a remainder of 0. In addition, I look at this and I say, well, the pattern that I have here is positive, negative, positive, negative. And the pattern that I also have is a growing pattern. When you have a growing pattern, just like the other one was a growing pattern, if I was to put a bigger number in here, then what would happen? Well, I'd have a negative 4 here, which would make a negative here. I would then make a bigger positive than the positive 2 that is here, which would make a bigger positive here than the positive 6 that is here. This would make a bigger negative when I multiply it times negative 4 than what I presently have. And so that pattern also, when you see positive, negative, and the numbers are getting bigger, also eliminates anything bigger than negative 2. So I can get rid of negative 4. So by doing 2 tests, I've gotten rid of 4 potential answers. Only ones left are plus and minus 1. I'm going to start with minus 1 just for fun. Carry the 1 straight down. 1 times negative 1 is negative 1. This is 0. 0 times negative 1 is 0. 4 plus 0 is 4. 4 times negative 1 is negative 4. Add them, I get 0. So what does that tell me? It tells me negative 1 here working. And negative 1 means I'm saying the thing that makes this 0 is negative 1. So that's the factor I'm talking about when I talk about negative 1 here. And that tells me that's one of the things that this factors into. The other thing that this factors into, I could do long division now, but I've already done the division here. This is remainder 0, this is the constant term, this is the x term, and this is the x squared term. So what I have there factors into that, meaning 2x plus 1 over x squared plus 4, x plus 1. Now, once I have done the synthetic division, I've figured out what the factors are, and I have factored it. Now what happens? Well, that I can see has the same characteristics as before. This came from two things that were fractions that were added together. And so I'm going to say, well, the denominators on these fractions, one of them will be x squared plus 4, and the other one will be x plus 1. And in the numerator, we've already seen these, we put something up here. But when we have an x squared here, before when we had just x plus 1 or x plus 3 or whatever, I only put a constant in the top. If I have x squared as my irreducible degree, then the numerator could be 1 degree lower than that. It was 1 degree lower when we had a constant. When we had just x plus 3 or something like that, 1 degree lower is a constant. Now we have x squared, 1 degree lower is a linear term. So it could be ax plus b, and then this side we'll just have a different constant. We'll say c, because that's 1 degree below. And so I end up, in this case, with 3 unknowns again. Now, I go through this. Again, what am I going to do? This is going to be multiplied by x plus 1 over x plus 1. This is going to be multiplied by x squared plus 4 over x squared plus 4, and I apologize for the lack of space, but it's the nature of our present situation. What I end up with is ax plus b times x plus 1. That's over this stuff. And I'm not bothering to write what's in the parentheses because that's going to go away. I'm not going to care about the denominator. And over here, c times x squared plus 4. Again, the denominators are all going to be the same, so the equations that I end up with look like this. 2x plus 1 equals, and I FOIL this, ax squared plus ax plus bx plus b plus cx squared plus 4c. I'm going to get an x squared equation out of this, an x equation, and a constant equation. The x squared equation is 0 on the left side, and on the right side it's a plus c. The x equation is 2 on the left side, and on the right side I have a plus b, and that's it, no c. The constant is 1 on the left side, and on the right, let's see, variable, 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 constant, variable, constant. 3 equations, 3 unknowns, but fortunately, in this case, it's not a particularly dense group. We don't have a, b, and c in every equation. So what can I do here? Well, I immediately see that a is equal to minus c. So I can put that in here and say, okay, I'm going to substitute for a. I'm going to say 2 is equal to b minus c. And my lower equation already said 1 equals b plus 4c. And I can eliminate b by subtracting. 2 minus 1 is 1. b minus b is nothing. Negative c minus 4c is minus 5c. This one's going to give us fractions. That tells me c equals negative 1 over 5. And immediately, a equals 1 over 5. Based on this. And we can go into here and pretty easily see that, well, if 2 is 1 over 5 plus b, that tells us b is 9 over 5. And we're done with the partial fraction decomposition there. Now, we're done with partial fraction decomposition. That's just the beginning of the problem because it's an integration problem, presumably, in this section. And so, what do we have? Well, we said this is equal to, which this is an integral. We'll assume this is integral dx. Then that breaks into the integral of, and we had ax plus b. So that is 1/5 x plus 9/5. And that was all over the x squared plus 4 term. That's one of the terms that I'm going to have, which then that can itself be broken into separate terms. And the other term that I had was plus c over, so c is minus 1/5, and that was over x plus 1. Again, constants and things like that are fairly easy for us to work with here. I'm going to pull a 1/5 out of the whole thing. So there's 1/5 here, 1/5 here, 1/5 there. So I pull the 1/5 out, and I'm going to break this into two separate fractions because this over that and that over that separately. So one of them is simply going to be x. I said x and wrote x squared. X over x squared plus 4 dx. That's integral number 1. Plus integral number 2, which is 9 over x squared plus 4. Plus integral number 3, which is minus 1, so I'm just going to make that a minus. And that is dx over x plus 1. And each one of these I can then integrate separately. And I took the 1/5 went from all of those. Okay. So what do these integrate to? Well, for this first one, this is u with a derivative on the top. Okay, if I on the first one, if I let u equal x squared plus 4, du dx is 2x, which means that dx is du over 2x. So as I rewrite this one, integral of, I've got the x, dx is du over 2x, which will cause those to cancel, and x squared plus 4 is u. So that's going to be a natural log. That one is du over u with a 1/2 term in there. This next one, of course, I can pull a 9 outside, and then I've got dx over x squared plus 4. That I should recognize as being inverse tangent. And over here, if I let u be x plus 1, that's a fairly easy one to see. Du and dx would be equal. That's going to give me natural log of x plus 1. Again, all this is going to be times 1/5. So what do I have? I have 1/5 times 1/2 of the natural log of u. U was x squared plus 4. Plus 9 times, and again, that's inverse tangent where x squared plus a squared, a is 4. So inverse tangent says 1 over a squared is 4, so a is 2. Inverse tangent of u over a, u is x, so it's x over 2. And then our last term is minus natural log of x plus 1. And that's it.